So I'm Kieran, I'm a third year PhD student at the University of Bristol, and my research focus is looking into aircraft emissions and how we can potentially mitigate non-CO2 emissions through changing the way in which we fly. So today I'm going to talk about my paper, which is looking into how we can mitigate aviation climate impact through basically controlled overlap of aircraft exhaust plumes. So first off, we're going to take a look at how aviation impacts the climate in terms of the science. So, of course, you've got emissions released from aircraft, and these emissions go on to perturb the chemistry of the atmosphere. And these perturbations can then go on to induce climate change through various climate forcing mechanisms. So the emissions in which we release, in an ideal world, we would simply see these four gases, so CO2, water vapor, nitrogen, and oxygen. However, as a result of inefficiencies and impurities in the combustion process, we also see the emission of NOx, carbon monoxide, hydrocarbons, soot, and sulfur oxides. So first up, we've got the emission of CO2 and water vapor, which are both relatively inert gases, so they simply go on to increase the concentrations of these gases in the atmosphere, resulting in climate change through the direct greenhouse gas effect. Next up, we got NOx and carbon monoxide, which aren't strictly greenhouse gases. However, they do result in climate change. Basically, they go on to contribute to climate change through increasing the levels of ozone and decreasing the levels of methane in the atmosphere. This is through the indirect greenhouse gas effect. Next, we have the emission of particles. So we got hydrocarbons, soot, and sulfur oxides, which increase the level of particles in the atmosphere, resulting in climate change through the aerosol effect. And finally, when you've got the emission of water vapor in sufficiently cold and humid environments, the water vapor can condense around the particles in the atmosphere, in the aircraft exhaust, resulting in climate change through the generation of contrails, which are clouds of ice crystals. Now, these contrails actually generate a warming effect because they're more effective at trapping heat within the atmosphere than they are at reflecting inbound sunlight. So how do these all add up in terms of their net warming effect? Well, there's a metric we can use called radiative forcing, and this is a measure of just how much a climate forcer blocks inbound and outbound radiation. So an example here is for contrails. So as I said earlier, you've got the ice particles, which are more effective at trapping heat within the atmosphere than they are at reflecting the sunlight. So if you've ever been to a talk on aviation and climate change before, there's a very good chance you've seen this figure. But for those of you who haven't seen it, this is just the contributions in terms of their radiative forcing. So contrails actually come out on top of any other type of emission from aircraft. So even compared to CO2, it's almost double the impact. Next up, we've got the greenhouse gases, so CO2 and water vapor, and then the indirect greenhouse gas effect through NOx emissions. Then we've got aerosols, and finally, the non-CO2 radiative forcing contributes 2/3 to the total climate impact of aviation, whereas the CO2 is merely 1/3. Is there anything that we can do about these non-CO2 emissions that we haven't necessarily implemented yet? And basically, due to the fact that the climate response to these non-CO2 emissions is highly variable with time and location, potentially there's something we can do there. So the non-CO2 climate impact is largely dominated by the NOx-based chemical reactions contributing 15%, and contrails, which contribute over half of the climate impact of flying. Now, these NOx effects and the growth of contrails, they grow strongly depending on the state of the atmosphere. So temperature, pressure, humidity, and chemical concentrations all determine the extent to which these emissions result in climate change. And of course, they vary significantly depending on when and where you release the emissions because of just natural variations in the atmosphere. So is there any way that we can exploit this spatiotemporal variability and use it to our benefit? There's a relatively well-researched concept known as climate optimal routing, which is effectively where you're rerouting aircraft to avoid these more climate-sensitive regions of the atmosphere. And this isn't just a small thing, this is potentially 20% that we could shave off of the climate impact of a flight for just 1 to 2% increase in fuel burn. And a lot of the times, even less than that. So this is huge. Like, if this was actually implemented, it could completely change the game. And the best part about it is that it's minimally invasive, so it doesn't actually require much new technology or infrastructure or equipment whatsoever. All it is just changing the way we fly. So ideally, we could see most of the fleet converting to these climate optimal routes by the end of the decade. And so we've got some various research initiatives going on worldwide. So TU Delft, DLR, NASA, a great research group called FlyATM4E, and also some live contrail avoidance trials that are currently ongoing in the Maastricht upper area control airspace. And as far as I know, these have gone relatively well so far. However, this approach really only considers the singular aircraft trajectories. So it doesn't really think about what is the state of the airspace in terms of the aircraft that are flying around in the same area. So I'm going to go on to explain why this might be a bit of an issue. So aircraft exhaust plumes exist for 2 to 12 hours post-combustion. And for most of that time, you have the emissions largely contained within the aircraft exhaust plume. So in areas of high air traffic density, where you might see a lot of exhaust plumes overlapping, this can of course result in the accumulation of these emissions and highly elevated concentrations of these emissions in the local airspace. And funnily enough, like, it's completely counterintuitive, but the overlap of 2 or more aircraft exhaust plumes can actually lead to reductions in the NOx and contrail effects. So potentially another 5 to 10% drop in non-CO2 radiative forcing as a result of simply overlapping plumes. The reason for this is that, first of all, the NOx, it can surpass its peak ozone production efficiency once you go past this compensation point. So it goes from an ozone production regime and dips into an ozone depletion regime. So the more NOx that you produce, the less effective that is going to be at producing ozone. And secondly, we see a similar effect with contrail growth. So when you generate a contrail in cruising altitudes of aircraft, the way in which this contrail grows is that it depletes the surrounding water vapor. So it literally dehydrates the local atmosphere. So that means that any contrails that you produce after that will have less of a climate impact because they don't quite have the same levels of water vapor to absorb. So is there any way in which we can exploit this further and then control the way in which we fly, so flying in formation essentially, to exploit this plume overlap concept? So here's an example of aircraft pushed to their minimum separation limits. So laterally, you've got 5 nautical miles, longitudinally 20 nautical miles, and vertically 1,000 feet. So you can see that in the lateral sense, you've got 2 aircraft flying parallel, and it would take about an hour or 2 for their plumes to eventually intersect. Vertically, it's a bit of a different story. The vertical dispersion rates are far less than horizontal, and the reason for this is due to the stratification of the atmosphere. So vertical mixing is relatively non-existent at these kind of altitudes. So that means that it would take over 10 hours to actually intersect those plumes. Now, when you look at longitudinally, even though it's the furthest distance apart, um, because these aircraft are traveling along very similar tracks, it means that they'll intersect plumes within just a matter of minutes. So the residual emissions from nearby exhaust plumes may also affect the optimized routes in which we could fly, which isn't really being taken into account in any current studies. So this plume overlap is most important within the first 2 hours post-emission. So this is roughly when the water vapor levels recover and the NOx in the system, in the saturated system, is fully reacted out. So my paper goes into exploring the likelihood for significant plume encounters, or SPEs, and their likelihood to occur in high-density airspace scenarios. So of course, using ADS-B data from OpenSky, we looked into basically air traffic characteristics and how we could potentially track aircraft plumes to see if this happens already, like in current air traffic today. So the first step was identifying high-density flight regions. So using the OpenSky data over the month of January 2022, I built up a heat map of air traffic density over this month. So this, you can see that the coverage is not great over anywhere that's not the US or Europe. But anyway, carried on the analysis just to find that, so yeah, the way in which it was done was all of the trajectories were taken from a slither of airspace, so plus minus 500 feet around flight level 380. And all of the trajectories were categorized into 1 by 1 degree longitude latitude bins. And from that, we found two hotspots which were worth looking into a little bit more. So that's the US and a European one. So the US one is somewhere over Florida, and European, I think it's north of Paris somewhere. So based on that, it was worth thinking about what's the best sort of time to look into to analyze these hotspots further. So plotted a map of, a plot of the average aircraft count for each hour throughout the day over the whole month. And you can see the US one around 8 a.m. was the hotspot there, just under 12 aircraft. And for the European one, it was just under 16 at 1 p.m. So taking these further and doing a sort of case study on them, we analyzed both the hotspots over a 3-hour period at their peak time, plus minus 1 hour. And this was the result. So this is all of the trajectories over those 3 hours, plotted on a 1 by 1 degree map. And on top of that, we use a relatively low fidelity plume modeling approach to capture the plume volume over time. So this is measuring the boundaries of the plume over time, and then just seeing visually whether they look like they're going to overlap. And you can see from the figures, looks quite promising. So the way in which this was done was that every 10 seconds throughout flight, so at a time step of 10 seconds, every plume instance was captured and a circle was plotted. And over time, these circles grow according to this plume modeling approach. And also at each time step, the relative distances and relative tracks between aircraft pairs were calculated. And using this, I came up with some sort of criteria to begin to quantify this data. So for every significant plume encounter, we can start to build up a bit of a better picture about just how likely it is for these plumes to overlap. So for an SPE1, for example, This is any distance under 20 kilometers between an aircraft pair, and the relative track and the relative bearing were within this hourglass shape that you see. SPE2 was similar, but it's instead of less than 20, it's anything between 20 and 50. And then SPE3 and 4 are basically the ones outside of the hourglass shape, as you can see. So using this criteria, thought we'd have a look into just trying to quantify the plume overlaps for these two hotspots. So here's the results here. So over this 3-hour period, we saw 41 aircraft in the US hotspot and 45 in the EU one. And the minimum distance between aircraft at any one point in time was 15 kilometers for the US and 11 for EU. The average distance was relatively similar, so about 48 kilometers. Relative track, so that was interesting. Because aircraft tend to follow very, very similar tracks and fly along corridors, we saw that the minimum track was almost reduced to 0. The average relative track, on the other hand, was very different between the two, because you can see that for the EU hotspot, we actually get a lot of crisscrossing of trajectories, whereas for the US one, it was all relatively straight, like just traveling from the top right to the bottom left. So we see a difference there of 15.2 compared to 148 degrees. And there's the sums of the SPE criteria. And so the interesting results here are that for the total SPE for the US hotspot was actually greater than that of the EU. Even though the EU hotspot had more aircraft, it looks like it's more dense. Because of this crisscrossing of trajectories, we don't quite see the same level of plume overlap. So that really goes to show that you're really prioritizing the heading, the relative track of these aircraft, because that's what really counts when it comes to overlapping plumes. So conclusions, based on the case studies, plume overlap is definitely possible and potentially already happening on quite a big scale. The SPE criteria gives us some sort of idea around just how many aircraft pairs may experience this. It shows that airspace density is not the only dominant factor in determining SPEs. So airspace complexity and relative heading can also play a key role. And finally, so future work, I plan to take this trajectory model and build it into a wider framework of chemistry and dispersion models, and hopefully use it to integrate plume overlap and saturation effects into these climate optimal routing studies. Okay, thanks for listening. Any questions?